also in 4.2, we're start talking about polynomial division. And so I know you guys have seen this before, but we're going to review. So if I have some x to the third, and I'm going to divide it by a linear, one of the ways to do it is to do polynomial division. So we have 3x to the third. Notice that right here I don't have any x squares written in there, so it's important that I put a plus 0x squared minus 2x and then a plus 5. And so just like regular division, I'm then going to put my x minus 3 on the outside. And I'm going to say, what times x gives me 3x to the third? So x times 3x squared gives me 3x to the third. And I'm going to write minus. Something I always do is put some parentheses in there. And then I'm going to multiply this 3x squared back to the negative 3. So I'm going to get minus 9x squared. Keep in mind I am subtracting here. So by design, this 3x to the third minus 3x to the third, that's gone. But I have to keep in mind when I subtract, I'm saying 0x squared minus negative 9x squared. So I have a positive 9x squared now. That sign changes when I have that minus the negative. So now I'm going to come back to my x, and I'm going to say x times what gives me 9x squared. And so x times looks like 9x. So I'm going to say plus 9x. So I'm going to get a 9x squared. I want to subtract. So I'm going to open up those parentheses. Now I'm going to multiply that 9x times the negative 3. So 9 times 3 is 27. So I have minus 27x. Now keep in mind, I am subtracting. So I have 9x squared minus 9x squared. That is by design, that goes away. Then I'm going to say negative 2x minus negative 27x. So minus the negative 27x becomes plus. So I have negative 2 plus 27. That gives me 25x. And then I'm going to bring down this 5. And so I'm going to say x times what gives me 25x. So it looks like times 25. So when I multiply that back out, I get 25x, but now I'm saying 25 times 3, so I'm getting minus 75. Keep in mind we are subtracting. I always put those parentheses in there so that I don't make a mistake and accidentally do the wrong operation on the second term. So 25x minus 25x, that's gone. That's on purpose. 5 minus negative 75, so it becomes 5 plus 75. That is 80. All right, so let's talk about what this means. It says determine the quotient and the remainder. So the quotient is the 3x squared plus 9x plus 25. The remainder is that leftover. So we got plus 80, and it's 80 out of x minus 3, that thing I divided by. So this is the remainder, and this one in pink, that is the quotient. So the quotient is that function you get. The remainder is the 80. Now that was a long, lengthy process. I actually don't enjoy doing polynomial long division. There's a couple times I will do long division, and we will talk about that as we progress through this unit. The method that I prefer is synthetic division. And so I know you guys have been exposed to synthetic division before. It's very similar. So when we do synthetic division, we use the 0 or the root. So whereas polynomial division uses the factor, this is known as a factor, synthetic division uses the root or the 0 of the function. And so if I think about x plus 2 equals 0, the number that I'm using where it crosses the x-axis is -2. That's the number that I'm going to use for synthetic division. It uses the 0 or the root. One of the ways it is typically indicates synthetic division, instead of having your division bar going up, a lot of times you'll see this as the division bar upside down. I have no idea. That's how I was taught. It's pretty standard. You see it in a lot of textbooks. So then we have the 5x to the third. We really only need the 5. Negative 6x squared. We only need the -6. Negative 28x. We only need the 28. Negative and plus 8. It's very important when we do this that we make sure that there's no powers missing. So we should always check. 3, 2, 1, 0. So we've got them all. If one of them was missing, we would have to put a 0 as a placeholder. If we don't do that, then we're going to end up with the wrong number. All right, so what happens is this first number is going to come down, and I'm going to multiply the 5 times the -2. So 5 times -2 is -10, and we are going to add these guys. So then I have -16. And I'm going to say -16 times -2 is a positive 32. And now I'm going to add -28 and 32 looks like 4. And now I'm going to multiply 4 times the -2, and I'm going to get -8. And I'm going to add these guys, and I get 0. So remainder 0, that means it goes into it nicely. What's left here is a quadratic. So this will show me that it factors into x plus 2, the original guy, and the quotient is 5x to the third, or sorry, squared now. We reduced it by a power when we pulled that out, 5x squared minus 16x plus 4. And so if I wanted to find the rest of the zeros, I could use the quadratic formula. On that guy, I could try to factor. I could try to complete the square. So we have some options from our last unit as to what to do. I'm not sure that this guy is factor friendly. If it's not factor friendly, I would probably use the quadratic formula to find it. So that is synthetic division. That is my preferred method. See how much little space it takes. Adding is always easier than subtracting. I really struggle, me personally. I struggle with this distributing the negative to both those things when I subtract. So just knowing me, that's where I make my mistakes. I tend to do a lot better with synthetic division. Okay, so one important idea from this section is something called the remainder theorem. So the remainder theorem is actually an easy way to figure out if something is a 0 or to even find out certain values of a function. So if I'm trying to figure out if -2 is a 0 of this function, I can use synthetic division. So -1, that's what we did in the last unit. Notice x to the third is missing, so I'm going to say 0 for x to the third. And then I have a 3 for x squared. I have a -4 for x and a -5 for the constant term. And I'm going to see, is -2 a 0? And so I'm going to use synthetic division to check it to see. So I have -1 is going to come down. -1 times -2 is a positive 2. I'm going to add, I get 2. -4, I'm going to add, I get -1. Positive 2, I get a -2 when I add. I get a 4, so I get a -1. So this has a remainder. And that tells me that it's not a 0. But if I take this function and I plug in -2, so if I plug in -2, so I have negative of -2 to the fourth plus 3 times -2 squared minus 4 times -2 minus 5. So 2 times 2 is 4, and 4 times 4 is 16, so this is -16. Negative 2 squared is 4 times 3 is 12, so plus 12. Negative 4 times negative 2 is a positive 8. And then I have a negative 5. So I'm thinking about this being a 20 right there. Negative 16 plus 20 is 4. So 4 minus 5, I get negative 1. Notice I get the same thing when I plug it in as I get the remainder. So if you have a really long function, what you can do is you can do synthetic division with that number that's the intended 0, and it will give us the y value of that function. And that should really make sense because if something is a 0, that y value for the remainder is 0. And so think about what that means. That means this is the y value at x equals negative 2 on the graph. And so this is true for all of them. So the reason we're getting a y value of 0 or a remainder of 0 is because it's on the x-axis, and that is where the y value is 0. So that's true for any of these functions. So if I go back and I look at the first one where I got a remainder of 80, this remainder of 80 right here, if I go to Desmos and I look it up in Desmos, I should see when I plug in 3, 3 is going to be the root, so I'm going to plug in 3 into Desmos, and I should see that I get a value of 80 coming out. So this is the function. Notice 80 is what comes out. In the second one that we had, we were looking at showing negative 2. Negative 2 is the one we just looked at that had a remainder of 0. Notice I've got a remainder of 0. And then this one that we just saw, we were looking at negative 2 again, and I get a y value of negative 1. So this is the remainder theorem. The remainder theorem says if you use division, if you use synthetic division, that remainder is actually the y value of that function. All right, example 5 is deciding whether or not a number is a 0 of a polynomial function. And so there's a lot of ways to do this. We could look at it graphically. We could do synthetic division. We could plug it in and see if we get a 0. So we're going to look at it a couple different ways. The first thing I'm going to do is try synthetic division, and then we'll look at the graph and compare the two. So for A, to use synthetic division, again, I'm just looking at taking the 0, or the intended 0, and I just need the coefficients. So x cubed is 1, negative 4 for the x squared, 9 for the x, and negative 10 for the constant. So we're going to bring down the 1. I'm going to multiply 2 times 1 is 2. I'm going to add, I get a negative 2. So I get negative 4. I get 9 minus 4 is 5. 2 times 5 is 10. I get a remainder of 0. So what that means is 2 is a 0 of the function, and we will look at that graphically also. All right, so when we look at this graphically, we can see that this is in fact crossing the axis at 2, which is exactly what we wanted to see happening. The second problem we're going to plug in and we're going to see is negative 2 a 0 of the function. So if I look at the second equation, is negative 2 a 0 of the function? So negative 2, it does not cross the axis here. The value at negative 2 looks like it is right here, and that is not 0. So let's see what happens when I do synthetic division and I plug in negative 2. All right, so problem B, we already said we did not see it cross the axis, but it was some weird number. So let's see what happens. So I have 3 halves. We can use 3 halves as is, or we can call it 1.5. I'm going to probably leave it as 3 halves for now, but when I start subtracting, I might change it. So just be on the lookout for that. 3 halves x squared minus 1, or sorry, 3 halves x cubed minus 1 for the x squared, plus 3 halves again for the x, and then we have a 0 for our last term for the constant piece. So the 3 halves is going to come down, and I'm going to say 3 halves times a negative 2 gives me a negative 3. The 2 Negative 2 cancels that denominator of 2, so I have just negative 3. I'm going to add this, I get negative 4. Negative 4 times a negative 2 is a positive 8. I'm going to write 8 as 16 halves. That is still 8, but I did that so I can add these. And I'm going to get 19 halves. Now I'm going to multiply that by 2. So if I multiply that by the negative 2, I get negative 19. And I'm going to add those. So it looks like my remainder is negative 19, which is about what we saw in the graph. But it took me a minute to toggle over. It was hovering somewhere around negative 19, but we didn't actually click on the negative 2. We could make a table and plug it in the negative 2 and see for sure what it is, but it was somewhere around there. So that holds true.